Hello everyone, my name is Bogdan Klinic and I'm going to talk about our paper called Arbitrary Decisions Are Hidden Costs of Differentially Private Training. Let's imagine a high-stakes predictive model used in a hospital environment which either recommends or not a patient to be admitted into intensive care. Let's say every patient is represented as a point in this illustration over here, and the model is represented as the decision boundary in the middle. If the point is above the decision boundary, then the model recommends to accept them, and if it is below, then it does not recommend to accept them. Let's look at this point over here. It should be admitted into intensive care, but the model has rejected them. And why is that? Of course, all models make mistakes, but what if there exists a very similar model, maybe with the same accuracy, that would accept the patient? The phenomenon that there could be different models that are indistinguishable in some way, like have the same accuracy, that have drastically different outputs for the same example, is called predictive multiplicity, and it's a measure of arbitrariness of decisions. In this work, we study a specific approach to train machine learning models called training with differential privacy, which is used when the data is privacy sensitive. And differential privacy does inject special noise during training, so that depending on the random seed, you could end up with this model or this model and this model. And you can immediately see that depending on the random seed, some predictions could be different for certain examples. So this is what we want to study. Our goal is to investigate the predictive multiplicity properties of differentially private training. So first thing first, we have to figure out how do we actually measure predictive multiplicity in our setting. And for that, we use a notion of predictive multiplicity called disagreement, which is based on prior work. It's a fairly intuitive notion. Basically, for any two models, f and f prime, coming from our training algorithm, we want to measure the probability that the decisions of these two models are going to disagree on a given example x. And the probability is over the randomness of the trained algorithm, which is what we want to study. Note that the data set S, we consider it to be fixed, and same goes for the input example x. All fixed, the only source of randomness that we consider is of the training algorithm. So how do we measure disagreement for differentially private models? Well, first thing that we show in the paper is that for a simple DP mechanism called output perturbation, we can actually have a closed form characterization in terms of disagreement, and you can check the details in the paper. But this is a very simple mechanism that is not practical. What can we do for more complex mechanisms that are used for let's say, neural networks and so on? Well, the parent work on predictive multiplicity in randomized settings has considered a Monte Carlo algorithm, and we can also do that. In our setting, Monte Carlo method is just a fancy way of saying retrain a bunch of models many times on the same data set. With regards to that method, we show a series of theoretical results in the paper that show how many times you need to retrain in order to estimate disagreement to a given level of accuracy. So even though the prior work has used the Monte Carlo method, we don't really know how many times you would need to retrain. So in our paper, we actually show how many, and we have a concrete guidance for that. Okay, so now we have a toolbox for estimating disagreement for differentially private models. Now let's audit some models, and we do that in 4 tabular tasks that represent high-stakes decision settings. 1 is in credit scoring, and 3 are in healthcare. So for each of these data sets, we train many logistic regression models with varying levels of privacy using a DP mechanism called objective perturbation. And for each level of privacy and each dataset, we compute the disagreement of these models. The first thing that I'm going to show is the relationship between the level of privacy and the performance of these models. So as you increase the level of privacy, you go to the right, you see that the performance invariably drops, and that's normal, that's expected, because the more privacy you have in differentially private training, the more randomness you need in the training process, and that destroys the signal, right? So in our roster of tasks, there are some tasks that achieve pretty good performance, such as the mammography models and dermatology models, and there are some models that do not perform well, for example, on the credit dataset. Now let's look at the disagreement values. So what I'm going to show now is the average disagreement on the test data set. Right? So we see that as you increase the level of privacy, you invariably get higher average disagreement for every data set and for every model, basically. So, and this holds both for tasks for which we have good performance and for tasks for which we have bad performance. For example, on the credit data set, our performance is not great, and we have disagreement close to 100%. Okay, sure, the models are bad, so the decisions are arbitrary. But this also holds for tasks where the performance is okay. For example, on the dermatology dataset, we have between 80 to 85 AUC here, area under the curve, which is a decent performance, I would say, on a tabular task. And at the same time, in the same privacy regime, we have 70% disagreement, which is fairly concerning. We also did the same audit for a close to state-of-the-art differentially private neural network on the image classification task. Unfortunately, I do not have time to go into details of this one, but we see the same trend. As you increase the level of privacy, you have higher levels of disagreement. What is interesting, however, here is that even though the levels of disagreement on this task are lower than the levels on the tabular tasks, there still are some examples which achieve 100% disagreement. And this is a trend. This is something that we see on all of our data sets. For instance, on the tabular tasks, even though for some of the levels of privacy in some of the data sets, the disagreement is fairly low. For example, on the mammography dataset, we have the best performance on these datasets in our roster of tasks. But you can see that even though average disagreement could be very low here, there are examples that attain every possible value of disagreement here between 0 and 1. The spread is huge. So this is also fairly concerning. So what have we learned in these audits? We have seen that higher level of privacy in differentially private training implies higher disagreement. And the disagreement also can be tricky to measure because it's distributed unevenly across the population. But so what, right? Actually, one could argue that high predictive multiplicity is good. And folks have done these arguments in the prior literature. High predictive multiplicity could mean that you're overcoming algorithmic leviathans. It could also mean that you're achieving individual fairness. And all of these arguments are fair, but they're not applicable to our setting of differentially private training. Unfortunately, I don't have time to go into detail, but in the paper, we argue that actually, in our setting of differentially private training, predictive multiplicity cannot be good. It's a concern, it's a normative concern, and it's a concern in terms of reliability because the models give out arbitrary decisions. And as a result, as a conclusion, we argue that before deploying differentially private models, we need to measure their predictive multiplicity. We need to audit their predictive multiplicity. And we ideally would want to also do that in deployment. Perhaps we could communicate the level of arbitrariness. We could communicate the level of predictive multiplicity to decision subjects. However, in differentially private settings, it's unclear how to do so because such communication would also leak information potentially about the training data. In conclusion, what we've done in this paper is we provided a provable way to calculate the required number of retrainings in order to estimate disagreement in randomized algorithms in general and differentially private algorithms in particular to any given level of accuracy. And this gives a concrete tool for practitioners that enables to measure disagreement, as I mentioned, in sort of audits. We have discovered that differential privacy invariably increases predictive multiplicity when the level of privacy increases across a range of tasks and models. And even if predictive multiplicity seems low on average, there exist examples and groups for which it is still high. This is what I've covered in the talk. In the paper, we also discussed the relationship between predictive multiplicity, accuracy, and privacy. And we have shown that the trends that I've shown before also hold even at the level of model confidence scores. So if we don't care about decisions, but the confidence scores, we still have higher multiplicity. So this concludes my talk. Thank you very much for your attention, and please check the paper for more details.